Ring laser. Ring lasers are composed of two beams of light of the same polarization traveling in opposite directions counter-rotating in a closed loop. Ring lasers are used most frequently as gyroscopes, ring laser gyroscope, in moving vessels like cars, ships, planes, and missiles. The world's largest ring lasers can detect details of the Earth's rotation. Such large rings are also capable of extending scientific research in many new directions, including the detection of gravitational waves, Fresnel drag, Lense-Thirring effect, and quantum-electrodynamic effects. In a rotating ring laser gyroscope, the two counter-propagating waves are slightly shifted in frequency, and an interference pattern is observed which is used to determine the rotational speed. The response to a rotation is a frequency difference between the two beams, which is proportional to the rotation rate of the ring laser Sagnac effect. The difference can easily be measured. Generally, however, any non-reciprocity in the propagation between the two beams leads to a beat frequency. Engineering applications. There is a continuous transition between ring lasers for engineering application and ring lasers for research. See ring lasers for research. Rings for engineering have begun to incorporate a vast variety of materials as well as new technology. Historically, the first extension was the use of fiber optics as waveguides, obviating the use of mirrors. However, even rings using the most advanced fiber working in its optimal wavelength range, e.g. OTWO at 1.5 mm, have vastly higher losses than square rings with 4 high-quality mirrors. Therefore, fiber optic rings suffice only in high rotation rate applications. For example, fiber optic rings are now common in automobiles. A ring can be constructed with other optically active materials that are able to conduct a beam with low losses. One type of ring laser design is a single crystal design, where light reflects around inside the laser crystal so as to circulate in a ring. This is the monolithic crystal design, and such devices are known as non-planar ring oscillators and pros or misers. There are also ring fiber lasers. Since typically the achievable quality factors are low, such rings cannot be used for research where quality factors above 10-12 are sought and are achievable. History. Shortly after the discovery of the laser, a seminal paper by Rosenthal appeared in 1962, which proposed what was later called a ring laser. While the ring laser shares with regular linear lasers features like extreme monochromaticity and high directivity, it differs in its inclusion of an area. With the ring laser, one could distinguish two beams in opposite directions. Rosenthal anticipated that the beam frequencies could be split by effects that affected the two beams in different ways. Although some may consider Masek et al. Has built the first large ring laser 1 meter x 1 meter. The U.S. Patent Office has decided the first ring laser was built under Sperry scientist Keo Chen Wang, see U.S. Patent 3,382,758 based on the Sperry laboratory records. Wang showed that simply rotating it could generate a difference in the frequencies of the two beams. Sagnac, an industry focusing on smaller ring laser gyros, emerged with decimeter-sized ring lasers. Later it was found that any effect that affects the two beams in non-reciprocal fashion produces a frequency difference, as Rosenthal anticipated. Tools to analyze and construct rings were adapted from regular lasers, including methods to calculate the signal-to-noise ratio and to analyze beam characteristics. New phenomena unique to rings appeared, including lock-in, pulling astigmatic beams, and special polarizations. Mirrors play a much greater role in ring lasers than in linear lasers, leading to the development of particularly high-quality mirrors. The resolution of large ring lasers has dramatically improved as a result of a 1,000-fold improvement in the quality factor. See Table 1. This improvement is largely a result of the removal of interfaces that the beams need to traverse, as well as the improvements on technology which allowed a dramatic increase in measurement time. See section on line width. A 1m×1m ring built in Christchurch, New Zealand in 1992 was sensitive enough to measure the Earth's rotation and 4mx4m ring built in wet cell, Germany improved the precision of this measurement to 6 digits. Construction. In ring lasers, mirrors are used to focus and redirect the laser beams at the corners. While traveling between mirrors, the beams pass through gas-filled tubes. The beams are generally generated through local excitation of the gas by radio frequencies. Critical variables in the construction of a ring laser include 1. Size. Larger ring lasers can measure lower frequencies. The sensitivity of large rings increases quadratically with size. 2. Mirrors. High reflectivity is important. 3. Stability. The assembly must be attached to or built within a substance that changes minimally in response to temperature fluctuations, e.g. Zeradur, or bedrock for extremely large rings. 4. Gas. Heme generates beams with the most desirable features for large ring lasers. For gyros, in principle, any material that can be used to generate monochromatic light beams is applicable. The laser beam theoretical tools. For a ring as a measuring tool, signal/noise ratio and line widths are all important. The signal of the ring as a rotation detector is used, whereas the all-pervasive white quantum noise is the fundamental noise of the ring. Rings with a low quality factor generate additional low-frequency noise. The standard matrix methods for the beam characteristics curvature and width are given, as well as the Jones calculus for polarization. Signal-to-noise ratio. Line width, line width, line width. Beam characteristics. The beam in ring lasers is typically excited by high-frequency excitation of a laser gas. Although it has been shown that ring lasers can be excited in all kinds of modes, including microwave-related modes, a typical ring laser mode has a Gaussian, closed shape. Given proper adjustment of mirror position, the analysis of beam properties, curvature, radius, width, position of wastes, polarization is done with matrix methods, where the results are distinct for circuits within mirrors. Typically, there are in wastes. For stability, there has to be at least one curved mirror in the circuit. Out-of-plane rings have circular polarization. The choice of mirror radii and mirror separation is not arbitrary. Curvature, radius, and width. Propagation of complex curvature. Polarization. Lock-in and pulling. The cavity. The quality factor Q of the cavity, as well as the time duration of the measurement, determines the achievable frequency resolution of a ring to a large extent. The quality factor depends largely on the reflection properties of the mirrors. For high-quality rings, reflectivities larger than 99.999% or equals 1-10 ppm are indispensable. At this time, the main limitation of mirrors is the extinction coefficient of the evaporated, high-index material Ti-Otwo. The size and shape of the cavity as well as the presence of interfaces also influence the quality factor. Quality factor Q. Measurement. Shape of rings. Mirrors. Large rings. Practical rings. Ring lasers are sometimes modified to allow only one direction of propagation by placing a device into the ring, which leads to different losses for different propagation directions. For instance, this could be a Faraday rotator combined with a polarizing element. One type of ring laser design is a single crystal design, where light reflects around inside the laser crystal so as to circulate in a ring. This is the monolithic crystal design, and such devices are known as non-planar ring oscillators and pros or misers. There are also ring fiber lasers. Semiconductor ring lasers have potential applications in all optical computing. One primary application is as an optical memory device where the direction of propagation represents either 0 or 1. They can maintain the propagation of light in exclusively the clockwise or counterclockwise direction as long as they remain powered. In 2017, a proposal was published to test general relativity by means of ring lasers.